Hello everybody, welcome on back. Biology of cells and tissues, we're talking about the digestive system. As always, if you have not liked the video, if you've not subscribed, do so now. As well, if you want to get copies of all of my notes, all of my updated everything, so that way you can add into them yourself, work through them, as well as have them available to study offline. There is a link in the description down below for you to be able to do that. So, continuing on to the large intestine. Functions of the large intestine. We're going to continue kind of the theme, the whole intestinal tract. Main focus is sort of absorption. So we're still in the large intestine. We're talking about specifically water absorption. We also get mucus production for lubrication, for protection. And then finally our feces formation. The macroanatomy, the gross anatomy of our large intestine. We have a couple different parts from the ileum. I can actually go back to the ileum portion really quickly. We can see that after the ileum, there is an ileocecal valve. Much like the pyloric sphincter, this is the crossover point connecting the small intestine to the large intestine, just like the pyloric valve connects the stomach to the duodenum. The different parts, we have first the cecum portion of the large intestine. We have the ascending colon because it ascends the body. We have the transverse colon because it transverses the body. Then we have the descending colon, and then finally the sigmoid colon. Sigmoid means S-shaped, so it's kind of shaped like an S. And then finally the rectum, and then the anal canal. So we will talk about each of these different portions going through the whole large intestine. A little bit more of kind of the gross anatomy of the large intestine. We have these structures called tinea coli. These are 3 bands of longitudinal smooth muscle in the muscularis externa layer. These muscles are slightly shorter than the rest of the tissue, and so it creates these pockets, or these pouches almost, these pocket-like sacs, what this that we call haustras. And then we also have these little appendages coming off. These are fat-filled pouches that are called epiploic appendages. Epiploic appendages is more just kind of like an extra thing. We don't really talk about them a whole lot. But the haustra and the tinea coli do play more of an important role within the large intestine. So you can see here, this is a slice taken, and this outermost layer, these kind of pocketings up, these are our tinea coli, and then those pockets are the haustra, and this is what we're going to be looking at. We have the resorption, or the absorption of water, some of the electrolytes, some of the stuff, compacting the food, because when it was in the stomach and through the small intestine, we're injecting fluids into it, putting enzymes in, putting stomach acid in, all of these things we're putting into it that contain water. And then we've absorbed all the nutrients out of it, and now we're going to take back the water so that way we can maintain more water in our overall body. Because everybody knows that none of us probably drink enough water. Here's your reminder. Pause the video. Go get some water. It'll help tremendously with studying. Okay, so looking at the large intestine layers, of course we have mucosa, submucosa, muscularis externa, and then the adventitia and serosa. The muscularis externa, we have an outer longitudinal layer, and then we have 3 bands of that smooth muscle fibers being the tinea coli. In the mucosa layer, there are no villi, because we're not looking to absorb a bunch of stuff, we're just looking to absorb water, and we have instead these intestinal glands. We have colonocytes, which are absorbing water, and we have goblet cells, which secrete the mucus, again to help things to be lubricated and as well as to be protected from the material inside of the large intestine. We also have an extensive diffuse lymphoid tissue in the lamina propria. So we have lymphoid tissue. Remember, lymphoid tissue was related to our immune system, and it's throughout the whole lamina propria, part of that mucosa layer. That is the mucosa. So here's the mucosa up here on top. Our submucosa, not much to report here. It holds all of that connective tissue, blood vessels, lymph, nerves, all that kind of stuff. Not worrying too much about the submucosa in the large intestine. I should say nothing special or different about the submucosa in the large intestine. Now, the muscularis externa, we have the inner, we actually have an inner circular layer. We have an outer longitudinal layer, and then we have the Teniae coli. The job of these Teniae coli is that they facilitate the peristalsis. Remember, we talked about peristalsis kind of being that squeeze and push forward to continue food and stuff moving along. We also have something, they do something that's called haustral churning. So essentially it's kind of like squeezing and moving everything that's inside of it. What is becoming and being produced as feces, it kind of squeezes it and moves it around so that way we can continue to absorb water from it. And then it also allows for what are called mass movements, which is what helps propel the waste, the feces, towards the rectum for eventual departure or elimination. Here's again kind of what all these layers look like. We have that inner circular layer, the outer longitudinal layer, the mucosa, the submucosa, all that kind of good stuff. Again, just a repeat of this. We have all the different cells in here, lymphatic nodules, all that good stuff. I'm actually going to remove this. I didn't complete this because I don't want to add too much onto this. There are a lot of conditions that have to do with the large intestine. IBS, irritable bowel syndrome, diverticulitis is another really common one. I don't want to get too deep into these. You're going to see a lot of this in future courses when you start you get into physiology, anatomy, and then pathology. You're going to start seeing a lot of this stuff pop up. I'm actually just going to go ahead and delete this out of the PowerPoint because I don't want you getting too far ahead of yourselves when it comes to this and not focusing on the foundational material. So this is still part of the large intestine, but we're moving on from the big portion, so all of this portion, and into more of what is the rectum, the rectoanal junction, which kind of includes the anal canal. So here, this is with the distinction that we want to make. So the large intestine is similar all the way through until we get to the rectoanal junction, and this is where we get a change in the epithelium. So it changes from simple columnar to stratified squamous. And we always think, why stratified squamous? Well, now we've removed all of the liquid from it. And as you can also see, we are condensing down. So we're actually getting a smaller amount of space. So there's more likely that there's going to be stuff contacting the sides, pushing against, as well as a little bit drier than it was in the rest of the colon or the rest of the large intestine. So we want to make sure that our cells are protecting the layer and that they can be replaced quickly. We also lose the muscularis mucosa as part of the rectoanal junction. So you can see here, this is from the rectum to the anus, all through here. You suddenly get a transition, you get a change from the columnar to squamous cell. The anal canal is a little subdivision of all of this. It's the last segment of the large intestine that opens to the body. And we have two sphincter muscles here. We have an internal anal sphincter, which is smooth muscle, which is under involuntary control. These are often asked as test questions, the voluntary versus involuntary control. Always remember, skeletal muscle is voluntary, smooth muscle is involuntary. So the internal is involuntary, external is voluntary control. This is kind of like if you've ever had you've been eating or something, especially post eating, you kind of, or after you've had your morning coffee or caffeine or anything like that, and you get that feeling of like, oh, I have to go to the bathroom. That's the relaxation of the internal anal sphincter, which happens involuntarily. And then we have to actually, to want to go to the bathroom, we have to voluntarily relax the external anal sphincter. Here's kind of all of the general anatomy of all of this. We have the rectum up here where the feces are stored. We have some muscles. We have the anal canal. Here are our sphincters. We have the internal anal sphincter and the external anal sphincter. Again, remember which one is voluntary, which one is involuntary, which eventually goes out and allows fecal matter to pass through the anus. And that is the whole GI tract itself. The last thing we want to talk about is actually bacterial flora. So within the intestines, there is quite a bit of bacteria, and this is actually good bacteria that we want. There's over 1,000 different types of bacteria, and there's 10 times more bacterial cells than we have cells in our bodies. So there's tons and tons and tons of microbes in there. Microbes enter the small intestine enter either from the small intestine into the large intestine or through the anus in order to colonize the colon. And this is typically in relation to our environment. Everybody has a slightly different bacterial flora. This is why if you travel to different countries in the world and you start to eat different food and eat different things, there's typically an adjustment period where you'll feel pretty bad for a couple of days eating the food that people around you are eating. And that's because there's different bacteria, there's different compounds, different foods that your body's not used to. So body's going to need some time to adjust and integrate some of the new flora into itself. Okay? But it's very, very important for our bodies to have a balanced bacterial flora. Some of the functions, we have vitamin synthesis. So some vitamins, like our B complex vitamins, as well as our vitamin K, is produced thanks to this bacterial flora. Previously, they used to think that about 50% of our vitamin K came from the bacterial flora. Like bacteria would grow, reproduce, and then would actually die and release vitamin K, and we would absorb it. They've now determined that it's definitely less than 50%. The scientific community still doesn't know exactly how much vitamin K comes from our bacterial flora, but needless to say, vitamin K is extremely important as it's actually needed to produce our clotting factors, as well as vitamin K is very closely related to a lot of our systems, like our energy-making system. In biochemistry, you will have talked about the electron transport chain and a specific component of that called coenzyme Q. Coenzyme Q is very similar in structure to vitamin K, and we need vitamin K in order to operate the electron transport chain to create ATP for our cells. So vitamin K, very, very important. The natural bacterial flora also acts as a defense system, like an immune system. Let's say immune system defender. So because the beneficial bacteria outnumber the pathogenic bacteria, they can suppress those pathogens that might slip in every now and then. And then our regular immune system, that lymphoid tissue that we have all through the large intestine, can destroy any bacteria that may get through the mucosal barrier. Gut bacteria and health. Overall, there's lots of evidence to support that a healthy bacterial flora allows for a healthy body weight, being susceptible to different diseases, even our mood. Having a good gut bacteria population and having a healthy population of bacteria in our gut is very, very necessary for us. This is also if you look at antibiotics, children especially, people who take a lot of antibiotics for conditions, so they take multiple doses or rounds of antibiotics, it's very, very common for those kind of people to have gut issues. As a matter of fact, certain intestinal issues, they think potentially even like celiac disease or those kind of conditions might be correlated to antibiotic use, like excessive antibiotic use in children. You can, like, leaky gut syndrome is another one that they'll talk about, where if you take a lot of antibiotics, it can damage it destroys the bacteria, which can have a very negative effect on your overall gut. So this is why, kind of as more conservative side of doctors, antibiotics 100% have their place in many, many, many conditions and are an amazing thing. But it's also something to make sure that we advise our patients appropriately and let them know, hey, what are the risks, what are the benefits of doing those things, and what other things can you potentially do to treat conditions that can be treated by antibiotics but may not need to be. Okay, again, this is a very fine line, or kind of the amalgamation of Eastern and Western medicine, conservative and non-conservative, conservative and invasive type medicine. So we need to be very careful on this line, make sure that we stay up to date on the research and the studies, and know what's best in how to advise our patients. We live in a world where research is becoming, or I should say information is becoming more and more difficult to find unbiased. And so we need to make sure that we are exceptionally good at sorting through proper research and unbiased research to make sure that we know what is best for our patients and the way that we should educate them and teach them how to educate themselves. Okay, finally, here is that last thing that I was going to show you guys. This gives us the most important information on each of the different layers of each of the different chunks. So this right here, this is perfect. Go through this. This is, as long as you understand and know all of the components in here, you should be pretty set as far as testing goes, as well as understanding the GI tract. Thank you so much for watching, and have a wonderful day, and good luck studying.